Okay, so in today's video, we are going to talk about the Lebesgue outer measure, and in here, this is where our interest really lies, because everything on the real, most of the things you're going to do on the real functions, has to do with measure theory. Okay, so now we are going to start the real deal. So now we are going to talk about Lebesgue outer measure, and first of all, this is what I'm going to explain. Let's say I have an interval AB. Okay, yes, I have an interval AB. Then I want to define the length of this interval. If I have endpoints, then the length of the interval, which is also known as the Lebesgue outer measure, is actually the difference between these endpoints. Okay, so this minus that gives you the Lebesgue outer measure of this whole set. So you're actually looking for the length from this point to that point, and you can actually see that it's a continuous line. There isn't any breakages anywhere, so you can actually find the outer measure of a continuous set. Okay, so a continuous set. So you want to have a continuous line, then you subtract the lower bound from the upper bound, and that gives you the outer measure. Okay, so somebody might ask, what if I have something like 1 to infinity? Then the outer measure is denoted by m star of the sets, or say the length of the set A. Okay, then this one becomes infinity minus 1, which is still infinity. So the outer measure of this kind of set is going to be infinity because it is unbounded. So any unbounded set, okay, has an outer measure of infinity. Okay, yeah. So basically you have the difference between the endpoints giving you the outer measure of it. So that's the definition of outer measure. But I want to define outer measure in a sense, a different sense, a very, very good but a bit complicated sense, but with illustrations you get to understand it very well. I am given a set, okay, a set A. This is a set A, or let me say I have a very big set. Let's say this is my real line. So negative infinity to positive infinity. Okay, yes. Then I can pick 2 points AB. Now if I want to find the outer measure of this, I know it is simply the point B minus the point A, but I want to define outer measure in a different manner. Now I am interested in having so many intervals such that the union of these intervals should cover A. So somebody can pick these intervals. I can pick this interval, these 2 intervals, like so many intervals, infinitely many. There could be many. Okay, so I can choose so many intervals like this, and you can actually see that the union is actually going to be from here up to that point. They are not disjoint. So let me try to draw something over here. They are not disjoint. The union actually is from here to that point. So you can actually see that the union of these intervals covers A. So let me call this part A. You can actually see that the union of I here covers A. So covers A. Okay, yes. So now that's what I want to explain. If I want to find the outer measure from this point to that point, I chose from here, like I chose these plenty intervals. Somebody can also choose an interval of say just from here to here, and another interval from say here to here. Okay, and you can still see that these 2 intervals are covering A. So there are so many collection of intervals. Okay, collection of intervals which can cover A. There are so many. So with this one, I can pick 2 and they will cover A. Somebody can pick 10 and they will cover A. Somebody can pick a whole lot of intervals which will cover this A. So that's what we are trying to do. So you have to pick a certain so many intervals such that the union covers A. Okay, so I have my first collection. I can pick first collection and 1. So I'm going to call this my first collection, and my first collection I had so many intervals. All right, I had so many intervals. I have all these intervals in here. Okay, yes. Then I have I, and let's say this is I and I, then I and maybe K, which is different, a different interval, another interval I, and say M. Yeah, so I have with this one I have so many I's, so 1 2 3 4. When I come to the second one, I have only 2, so my K is going to run from 1 to 2. Somebody can pick M, so it's going to have different intervals running from a certain 1 to a certain number. So I hope you're getting it. That's like you choose a number of intervals such that the union should cover A. That's what I'm trying to say here. Then what I'm saying is going to be the outer measure of A is that I will pick this interval. I'll find the outer measure. The outer measure of that, the outer measure of these intervals. And you know that is going to be the endpoints, the difference between the endpoints. So this minus that point, this minus that point. I'm finding the outer measures of each one of these here. Okay, so once I'm able to find all of them, I find that of these two sets of intervals too as well. So I find this minus that, and that is giving me a collection. This is a difference. This is a collection on its own from here to this point. It's a collection on its own. So I'm very sorry, but then from here it's a collection on its own, right? Yes. So this is a collection on its own, and that is a collection on its own as well. So I find the outer measure of this and of this interval and that interval. Then I'll do so for these ones as well. So there are possibly many sets of interval you can look for. Okay, then we are going to do for each one of them. So what I'm going to do is that after finding the outer measure of this set, each one of them, I will sum all of them. I sum all of them, and that's going to be my first sum. Okay, so I'm going to look for summation of the outer measures of I and 1, summation M star of I and 2, I and K, sorry, this is I, sorry, the summation M star I and M. Okay, so let's say these are the possible intervals you can get which will cover A. These are all of them. Okay, then if I am able to find all these sums of outer measures, the one with the least value I'm going to have here should be the outer measure of A. Are we getting it? So what we are actually saying is that this is going to be the infimum, which is the smallest, the infimum of the summations of the length or the outer measures of the intervals, given that A, we know that from this definition we are saying A should be covered by the union of the intervals over here. So given that A is contained or is covered by the union of the I's. Okay, so this is a definition for outer measure. When you pick infinitely many collections or the possible collections of intervals which are going to cover A, you find the outer measure of each one of them, the outer measure of each interval here, then we are saying that if you are able to find the sums of all the possible intervals, the infimum, the smallest of them, the infimum of it is actually going to be the outer measure of A. Okay, so that's the definition of outer measure. So there will be proofs that we are going to have, but I want to talk of certain properties of outer measure. Now, the first property of an outer measure is that the outer measure of an empty set is always equal to 0. And there is a difference between outer measure and a set being measurable. The fact that the outer measure is 0 doesn't mean it is not measurable. Okay, and we are going to do that proof in some videos to come. But the outer measure of phi, or the outer measure of this empty set, is always equal to 0, and we are going to do the proof in the next video. And the second one is that the outer measure, if A is covered, or if A belongs to B, okay, then we are saying that the outer measure of A should be less than or equal to the outer measure of B. So we are going to prove this as well. So it actually makes us know that outer measure is monotonic. So if it is monotonic, then it actually means it has a certain direction with which it's increasing or decreasing. And it actually means that if I pick a set B, let me say I have a set A, okay, and this is covered by B. We know that B covers A, hence the outer measure of B should be greater than the outer measure of A. In the same way, if I pick C such that this B is, let me make it D so that you don't get confused, it's contained in D, since B over here covers A with the outer measure being greater than or equal to A, the outer measure of D should also be greater than or equal to A. And that's what we are saying, or that's what we mean by the outer measure being monotonic. Once you have a set greater than a set which is greater than a set, the outer measure of the biggest should also be greater than or equal to the outer measure of the smallest. Okay, so in our next video we'll be doing so many proofs, we'll be meeting so many proofs, but this was just to make us understand what the outer measure really was. So see you in the next video. If you really like my content, you drop a like and subscribe to the channel. So see you in the next video.